Okay, so let us cover capacitance review. We will do last class and then we will move forward. Okay, so capacitance, it is the charge storing capacity of a conductor. Okay, so suppose if there is an isolated conductor and you are giving some charge you are giving, that charge will go only on the surface. Why? Because this is the property of conductor, charge cannot go inside that, so charge will remain on the surface and it will develop a constant potential. So capacitance is defined as charge by voltage, ratio of charge and voltage. Okay, and we have seen for a spherical, let us say radius is r, spherical conductor, if you give a charge of q, it will develop a potential as kq by r. So capacitance is the ratio of charge and voltage. Charge and voltage ratio become r by k. K is 1 by 4 pi epsilon naught, so this become 4 pi epsilon naught r. So this formula 4 pi epsilon naught r is the capacitance of a spherical conductor. Okay, then we go into the parallel plate capacitor. Parallel plate capacitor. Parallel plate capacitor is made up of two parallel plates, like one plate and another plate. One has plus q charge, another has minus q charge, right? So here on the surface it has plus q charges, here it has minus charges, and the distance between the plates is d. Area of the plate is a. So what is the capacitance of this parallel plate? Two plates are there. Note that there are two plates. What is the capacitance of this system? Okay, so how can we find out? So for two plate system, we have to write capacitance as charge by potential difference. This ratio will be called capacitance, charge by potential difference. So let us say this is the first plate and this is the second plate. What is the potential difference? Note that this is potential difference, so it is always positive, it cannot be negative. It is not the change of potential, it is potential difference. So higher potential minus lower potential, higher potential, positive plate is higher potential, negative plate is lower potential. This is what is potential difference. How do you calculate potential difference here? So you remember, now if I want to use potential difference, I can go from this point, I can move from this point to this point, because you are going from lower potential to higher potential. So change of potential delta V, if you remember, we can calculate minus E dot dr. And what is the direction of electric field? You can move this way displacement, but electric field, you know how electric field is existing. Electric field goes from positive charge to negative charge. So electric field is existing in this direction, and electric field between two plates we have calculated, which is sigma by epsilon naught. Sigma is charge by area epsilon naught. So this is electric field. Now let us apply this in the formula delta V. So delta V here is equal to minus electric field is this direction and d delta R in this direction. So you are going opposite. So dot product will give minus 1 itself. So there will be minus E delta R. Minus 1 is plus, electric field is Q by A, right? And delta R is the distance here d. So this is delta V. So tell me what is capacitance now? Capacitance is the ratio of charge by potential difference. So capacitance, which is charged by potential difference. Now let us substitute potential difference. Substitute potential difference. So Q by QD by A epsilon naught. Q get cancelled. Epsilon naught E by D. This is what is capacitance. So for parallel plate capacitor, right, this is how the capacitance is calculated. We are just doing review, right, because we have forgotten things. There have been gap. Okay. So parallel plate capacitor is given by this formula. Uh, then there are different types of capacitor. Now let us try to go for spherical capacitor and cylindrical capacitor, and we will write the formula. We will derive the formula for that. So now we will going to spherical capacitor. Spherical capacitor. So there are two spherical plates like this. One radius is A, another radius is B. Bigger sphere has radius B, right? And let us say that it has charge plus Q spread here, plus Q charge is spread here, and minus Q charge is on the inner surface. Minus Q charge is there, minus Q. Now again, how to calculate capacitance of spherical capacitor? Same way, capacitance is charged by potential difference. Okay, this is the method. Now here let us say this is the first plate and this is the second plate. Means first conductor, second conductor. Potential difference means V1 minus V2, right? Potential difference means V1 minus V2, because V1 is positive plate and this is negative plate, so higher potential minus lower potential. Okay, so how do we calculate potential difference? So first we need to calculate potential of each. So let us write potential of each. V1. How do you write potential of this surface? Any point on this is same potential. So potential of this one is 1 due to itself plus potential of 1 due to the second charge. So its own charge is creating here potential and the outer charge is also creating potential here. So total potential here you have to calculate using this. Okay, so potential due to its own charge, so kq by r, kq by r means radius is J, plus potential here due to outer charge. So this point is inside the outer surface, so it will have same potential which is same at the outer surface. So k outer charge which is minus q, k minus q by this radius is b, right? So this is v1. What is v2? Same manner v2 you calculate potential of 2 due to the second charge, due to the first charge, right? V2 due to 1 plus V2 due to 2. So let us calculate. So here you want to calculate due to the inner charge, so kq by outer radius, kq by outer radius plus here its own potential, so k minus q by its radius b. So you got V1, V2. Now tell me what is V1 minus V2. Tell me what is V1 minus V2. Do V1 minus V2. This is V1 minus V2. So you can see the second term is same. Second term will get cancelled. First term will be there. So this will become KQ by A minus KQ by B. You can take KQ common and do LCM, B minus A by AB. Right. So you got the potential difference. Now apply here in the formula. So capacitance is equal to charge by potential difference. Substitute this difference, KQ B minus A by AB. QQ got cancelled. 1 by K is 4 pi epsilon naught. So 4 pi epsilon naught AB by B minus A. Done. This is a spherical capacitor. We have done already all this. Okay. Over. Then now cylindrical capacitor we have not done. Now we will do cylindrical capacitor. Cylindrical capacitor. Suppose this is one cylinder and this is another cylinder, and let us say inner cylinder has radius A, outer cylinder has radius B, and the length of this cylinder is L. This is the axis of the cylinder. Inner cylinder has charge plus Q, outer cylinder has charge minus Q. Again, how to calculate capacitance? Capacitance is charged by potential difference. So let us say inner is first plate, outer is second plate. So potential difference we have to calculate V1 minus V2. V1 minus V2. How do we calculate the potential difference? Think about it. We can, the general approach is to apply the idea of delta V minus C dot dr. So to do that, how do we know that electric field? For electric field, you need to derive electric field by taking a Gaussian surface. Suppose this is a point P, which is at a distance of r. So try to make a Gaussian surface. Let us make a Gaussian surface, and that Gaussian surface is also going to be a cylindrical surface. Same cylindrical surface you make. A Gaussian surface I am making now. This is a Gaussian surface. Gaussian surface. Apply Gauss law. Gauss law, you remember what it is. Gauss law. Gauss law says that net electric flux is charge inside pi epsilon naught. Charge inside this surface is the total charge, which is the inner cylinder charge, which is capital Q by epsilon naught. But how do you calculate flux? Flux calculation, if you remember, here we can divide the total flux into three surfaces. One will be this surface, Gaussian surface. Let's say consider this as the first surface, bottom surface, this one, second surface, and this curved surface of cylinder, Gaussian surface. This is third surface. So if you remember, how are we calculating this? So electric field is going radially away. So this electric field lines will be going radially away. So this area vector, when you draw this area vector, this is going to be perpendicular 90 degree. Here also the area vector and electric field lines will be perpendicular. So this is going to be 90 degree. So flux is flux 1, flux 2 plus flux 3, and we know that flux of 1 and flux of 2, flux through 2 is going to be 0. Why? Because dot product of field and area vector are perpendicular, you know that. So there is no flux due to this first and second surface, but third surface we will have flux, because electric field lines are going like this, and area vector is small area vector will go like this. So third flux will be there, which will be integration of EDA, and this integration will give each constant area, curved surface area of a cylinder. Remember, curved surface area of cylinder 2 pi r into L. This is what it is. So this, now you can substitute it here, substitute all these values in the Gauss law. So you will get E into 2 pi r L is equal to charge by epsilon naught. So from here you get the electric field. Electric field is going to give us as charge by 2 pi epsilon naught r L. This is the electric field. Electric field is given by this, right? Okay, so you have got electric field. Now you will use electric field as minus dV by dr. So let us say you are going from higher potential to lower potential. So you will write as, in the direction of field you are going, so you will write as delta V as minus E, integration of minus E dot dr. So delta V means you are going from first to second, so you can write V2 minus V1 is minus electric field will come out, integration of No, electric field is a variable here. It cannot come out. It will remain under integration. So E dr. Let us do this integration. This minus sign you can bring this side. So V1 minus V2, which we want delta V. Electric field is what? Q by 2 pi epsilon naught R times L into dr. So do the integration. Integration become 2 pi epsilon naught L. 1 by R integration become ln R. ln R, and you are going from where to where? You are going for a radius of a small radius A to B. So this limit is also from A to B. So this is limit from A to B. So from here, what is delta V? Delta V comes as charge by 2 pi epsilon naught L ln B by A. Right? Now this is a important, derivation which we have done. Now let us calculate capacitance. So what is capacitance? Capacitance is Q by delta V. So what is Q by delta V? Q by delta V will become 2 pi epsilon naught L divided by ln V by A. This is the capacitance of a cylindrical capacitor. Are you clear about this? Yes. Okay. So these important derivations we have done. Okay. Then now parallel plate capacitor, series and parallel. We will discuss series and parallel. Series combination, parallel combination. Series combination, parallel combination. So series means, let us take example, two parallel plate capacitors are like this and it is connected with a battery. Battery voltage is V minus plus. So what happens is that this will be sending some charge here. So some plus Q, minus Q, plus Q, minus Q. So remember, in series each capacitor has capacitance C1, C2. So each capacitor has same charge. Each capacitor has same charge. Same charge. Also note that suppose the total voltage is V, so potential difference across this is V1, potential difference across this is V2. Okay, so potential difference, total potential difference V is equal to V1 plus V2. We should note this. Now you can ask how this is coming. This idea comes from voltage rule. Remember voltage rule. The voltage gets divided. Voltage gets divided in this circuit. Okay. So remember how this is coming. You can think about it. So this voltage is the voltage difference between these 2 points. So voltage difference between these 2 points is sum of voltage difference between this and this, and between this and this. Okay, this is the voltage difference. We'll discuss afterward Kirchhoff law also. You see this derivation, but this is the rule here. Voltage rule will apply here. Okay. Then what is called a equivalent capacitor. Equivalent means these two arrangement can be replaced by a single capacitor, which you can call a C equivalent, and the same battery will be connected here, and the same charge plus Q minus Q, right, will be there on each other, and this plus minus. So that C equivalent is a single capacitor which is connected with same battery. It is having same charge which in this series they are having. So you can replace these two with a single one, that is called C equivalent. Okay. So C equivalent means it's a equivalent of this system. It is like a equivalent system it is. Okay, then okay, now try to apply. Suppose if I see the equivalent, q is equal to capacitance is equal to what? C is equal to q by v, q by v. So v is equal to what? V equal to q by c. So this v can be written as q by c equivalent, and this v1 can be written as q by c1, and this v2 can be written as q by c2. From here only we get the important result. What is that result? That 1 by c equivalent is 1 by c1 plus 1 by c2. This is what in series happens. Because same charge is there on each of them, same charge is there, so we can remove the charges, cancel out, and this result comes. Okay, this is the result in series. Also note that what is v1 and v2. Now try to write v1 and v2. So from here you can solve C equivalent. So from here C equivalent comes as C1 C2 by C1 plus C2. Now I want to calculate V1. So V1 is what? What is V1? V1 is Q by C1, right? And what is Q? What is Q? Q can be written as C equivalent into voltage by C1, right? Because Q by C equivalent is V, or Q by V C equivalent, so Q is C equivalent into V. Now what is C equivalent by C1? That will become C2 by C1 plus C2 times the total voltage. This formula you have to remember definitely. Without this you cannot solve. So V1, this is how V1 you can write. V1 will be second capacitor by sum of capacitor into total voltage. Similarly, what will be V2? V2 will be Q by C2, and Q is C equivalent into V by C1. Now C equivalent by C1 will be C equivalent, sorry, C2. This is C equivalent by C2 will be C1 by C1 plus C2 into V. Are you getting this? Yes. So this is how the voltage gets divided in series. We must remember this formula. V1 is C2 by C1 plus C2 into total voltage. V2 is C1 by C1 plus C2 into total voltage. This formula is very, very important. We'll directly use this formula. Okay, done. This is series is over. Now parallel, let us discuss. So in parallel, what happens is we will have two capacitors like this way, and this system is connected with a battery. Again, the equivalent will be, there will be a single capacitor and the same battery is connected, and same charge plus q minus q will be there, which this entire battery is sending. This battery is sending plus q, and this battery is sending minus q. Same thing here also, but now this is equivalent of the system, equivalent. So this is first capacitance, second capacitance, but note that here this charge which is going here, this plus q, will get divided into two branches. It will go q1 and here it will go q2. So charges will divide, and this is plus minus q1 q2. Here it is plus minus q2, right? So plus q2 minus q, here plus q1 minus q1 plus q2 minus q2 charges. So you can also say that this minus q charge which is coming here, it is getting divided here into this branch minus q1, this branch minus q2. So this rule is based on junction rule. The charge is getting divided. So one thing that you have to note is that this charge q can be written as q1 plus q2. And another important point to note here, that the same potential difference, battery voltage, same battery voltage will be there. So here the voltage difference is also V, here also the voltage difference is V. So you can note that the in parallel, same potential difference, difference across each capacitor, Across each capacitor we will have same potential difference. Okay. Now try to do this derivation. Hmm. Charge may be equal if both the capacitors are same C1 C2 are equal, then equal charge will divide, otherwise charge will be not equal, correct? Okay, so now let us apply. So again q we will write as C equivalent into voltage. Q will be C into, so let us write this in terms of equivalent, C equivalent into voltage. Q1 we will write C1 into voltage, Q2 will write C2 into voltage. So here voltage are same, so they get cancelled. So you got this result, C equivalent is C1 plus C2. So in parallel C equivalent will be C1 plus C2. Now as you asked that how much charge will go in the upper branch and how much charge will go in the lower branch, let us calculate that. Very easy to calculate. Okay, so let us take charge in the upper branch Q1. So this charge Q1 will be C1 into voltage V, right? C1 into voltage V. But I want to write this in terms of the total charge. How much fraction of total charge is going in the upper branch? So voltage we need to replace. So voltage I can write as Q by C equivalent. Q by C equivalent I will write, because V is equal to Q by C equivalent. Now C equivalent will substitute. So this will become C1, C equivalent becomes C1 plus C2 into the total charge. Right, so this is how the total charge gets divided in the upper branch. Upper branch charge will be, upper branch capacitor C1, so charge gets divided proportionally to the capacitor. More capacitor means more charge, less capacitor means less charge. So upper has capacitance C1, so charge will be C1 by C1 plus C2 into total charge. Similarly, charge on the lower capacitance Q2 will be C2 into V, and V again you write as Q by C equivalent. Now C2 by C equivalent is C1 plus C2 into the total charge. So total charge on the second is C2 by C1 plus C2 into total charge. Charge on first is C1 by C1 plus C2 into total charge. Right, it is similar like how did you divide voltage, but here voltage 1 was depending on capacitance 2 and voltage 2 was depending on capacitance 1. That's the difference here, right? Clear? Yes. So this is all about series parallel storage over. Then we can see many other laws are there. We will be seeing that. But before we go into that, we had to discuss a very important thing regarding last class. I told that we will discuss about this capacitor, spherical capacitor, where first case 1, where inner is earth, let us say its radius is a and outer radius is b, right? And outer is given some charge q. Okay, this case. Another case I told that uh, two capacitors are there and outer is earth now and inner is given a charge q. This radius is small a, this radius is small b. So this is the case 2. So case 1 is uh, inner is earth, inner is earth, and outer is charged. And here inner is charged and outer is earthed. Okay, sorry, outer, correct, inner is charged, outer is earth, right? So these two cases I told how to calculate the capacitance of these two systems. Okay, so what I told here is I'll just give brief idea about how to derive it. What I told is, suppose we have already derived, like for example, if there is a capacitor of radius r, we write its capacitance as 4 pi epsilon naught r. Correct? The capacitor of radius r is this. How do we write it? Okay, how do we write it? Here you have given some charge to this. So how do we write it? We have seen its derivation, but let us try to understand in terms of one sphere kept at infinity. So another sphere, you can consider that another sphere is kept at infinity, and this is plus q, then that has minus q charge. Minus q charge, because when you bring this charge, from where are you bringing? You are bringing from infinity. So when you are giving this charge to this capacitor, right, so you are developing a minus q charge, because initially this entire system is neutral. So you cannot create charge. Total charge of system is still 0, plus q minus q 0. So you are bringing charge from infinity to this. Okay. So this, how did we derive it? So this idea is that, if you remember that formula, 4 pi epsilon naught AB by B minus A. This you can also write as 4 pi epsilon naught. B is infinity here, so divide by B, so 1 minus A by infinity. 1 by 1 minus A by B. So note that if the outer radius, which is B here, that B become infinity, means this term will become 0, so it will become 4 pi epsilon naught A, because here B is becoming infinity, right? This is what it is. So this we have derived, this formula we have derived. Now you can assume that a single capacitor, spherical capacitor, is nothing but it is two capacitors are there. Second, we are not able to see because that is at infinity. Okay, so if you apply that logic, you will be getting this formula. Okay, now how can we transform this into a parallel plate capacitor? Okay, so what is this means? Here note that if I say that this potential of this surface is V1, this potential is V2, so V2 is like 0. V2 is like 0. So these are two different plates you can take. One plate is having a potential, so let us call this as point 1, and this is cell 2. Two plates are there. So you can connect it like this. Okay, and first plate, this first plate is connected with a battery, and second plate is connected like this. First plate is connected with battery, and this, so this is what is V1, and this is V2, which is 0. So the voltage difference across this is V1 minus V2, right? So you can transform this system into a parallel plate. It's a very good technique. By using this, you can derive many results, many calculations can be done. Okay, so the capacitance of this parallel plate capacitor can be written as 4 pi epsilon naught, 4 pi epsilon naught R. So we can transform a spherical capacitor into a parallel plate capacitor system like this, and we can solve circuit type of question, circuit based questions, right? So this is an important idea. Now let us go to this, and try to figure out here the idea. Suppose if I give here this one, I am taking, this is V1, this is V2. So here V1 is 0. V1 is 0, and now you will say that where is my third capacitor at infinity? You make a capacitor at infinity, you draw a capacitor at infinity. Okay, like this. This radius is infinity. This radius is infinity. So now if you are saying here charges, what are the charges? You have given charge here, right? You have given charge here. So how the charge will induce? Note that this capacitor which is at outer, you can take is V3. So this is one surface, second surface, and third surface, but V3 must be 0. V3 must be 0. What is, why 0? Because it is infinity. Infinity potential is 0, we know that, right? Potential at infinity is 0, we know that. V1 is also 0 here because it is grounded. V2 we do not know what it is. Okay. So here, suppose if you take a charge, let us say charge small q, you take plus small q. So inner surface must have minus small q, and the remaining charge should go here q plus q, right? Because some of the charge must be 0 here, so due to induction plus minus is happening here, plus q should remain, and then induction will happen between this and infinity. But note that they have given that this potential v1 is 0. Let us try to do that. Let us calculate v1 first. What is v1 here? So potential of 1 will be potential of 1 due to its own, we know already, but potential of 1 due to 1 you can write, plus potential of 1 due to 2 you can write, plus potential of 1 due to 3 you can write. Okay, you can write all this. Now tell me, potential of 1, you know already it is 0 because it is grounded, right? But what is potential of 1 due to 1? Due to 1 itself. Huh? So on this one, charge is plus q. So kq by radius, which is a, plus potential here due to the outer surface. Outer surface is charge capital Q. So k capital Q by radius p. And this one, some charges happen, but its radius is infinity, so it is 0. It is going to be 0. Now, from here, what do you get? From here, what do you get? We can get relation between capital Q and small q, right? We can get relation between capital Q and small q. Okay, but what will happen with that? Nothing can happen with that. Leave this part. Okay, why do we do that? Because we know some charges are there. What we want to calculate, capacitance of this system. Okay, so what I told is we can get relationship between capital Q small q, right? We can find out, but what we want here is try to make a circuit with capacitors. So let us try to do that. So how many potentials are there? V1, V2, V3, and V1 and V3 are equal. Try to do that. So V1 and V3 are equal to 0, and this side I am taking as V2. Right now, try to do the capacitor. Try to build capacitor between these 2 points. Can we make capacitor? So if you see here, this space between first and second is also making a capacitor, right? It is between first and second. So between first and second, you make one capacitor. Let us call this capacitor C1. This is C1. Now between second and third, there is another capacitor. Let us call this as C2. This is also between 2 and 3. Between 2 and 3, you make another capacitor like this. This is C2. Clear? This is C2. Now these two are what? These two are in parallel. Parallel means what? It will be C equivalent. C equivalent can be write as C1 plus C2. Yes. Parallel means this is what is equivalent of this system, C1 plus C2. Okay, so can we now calculate C1? C1 is in between this and this now, so we can use this formula. C1 is 4 pi epsilon naught. This radius is A, this radius is B, so AB by B minus A. Right, this is C1. What about C2? C2 is between this and this, so outer is infinity, so this is due to only this one, which will be 4 pi epsilon naught B. This is what it is, 4 pi epsilon naught B. Now try to solve this. Okay, this is a very important technique. Now try to find out, this will be the answer. Calculate. So C equivalent of this system will be, you can take 4 pi epsilon naught B common. So it is A by B minus A plus 1. So A will get cancelled here. So you will get C equivalent as 4 pi epsilon naught B into B square by B minus A. Clear? So this technique is not given in book. This I have recently found out, this technique. How to convert a spherical capacitor into a parallel plate capacitor, and you can derive this, just like this you can derive. Otherwise integration and all this is very difficult to derive. Just by series parallel we can derive it. Good technique it is. Okay, second, same technique you can apply here also. In this case, what will happen? How will you apply that? Here also you take infinity. As I told, na, you have to take infinity, you take that. Take one capacitor at infinity. Okay, but how will you take charge distribution here? Charge distribution is important. So here capital Q is there, na. So this side you have to take minus Q. This side charge you do not know. Let us say this side charge is small q. Plus q. You don't know. But one thing you know, if you are taking this is V1, this is V2, V2 has to be 0 because it is earth, and V3 has to be also 0. Now, yes, what I was doing there, here we have to do. What is this small q that you try to first find out? What is that small q? So, because V2 has to be 0. And what is V2? So, potential here will be potential due to this one, potential due to itself, right? And that will not create potential. So, you can write V2 due to 1, V2 due to 2 plus V2 due to 3, right? But when you write V2 is 0, but V2 due to 1 will be K capital Q by B plus due to this itself. So, K minus Q plus small q divided by B, and this potential is 0 here because this is at infinity. So, from here what do you get? You definitely get that small q has to be 0. Are you getting this? Small q has to be 0. That means there is no charge here. There is no charge. This charge is 0. Only charge present is inner surface here and outer surface here. This is the only charge in this case. Okay. So, if you want, you can also again say here that this is capacitance C1 and this is capacitance C2. And now again try to bring it in terms of parallel plate capacitor. Okay. Try to draw that circuit, parallel plate capacitor. We'll draw that side. So this is voltage V1, V2, V3 0 here. So V2, V3 I will put here. V2, V3 equal to 0 this side. Okay. And this I will put as V1. Now try to put capacitors in between them. This C1 is between V1 and V2. So between V1 and V2, you put one C1 capacitor. Okay. And this capacitor C2 is between V2, V2. Now this is what you have to understand. If you want to put a capacitor between V2, V2 means you can put it like this. You can put it like this. It doesn't matter because the capacitor is between same points, same potential. This will not store any charge. It is a redundant circuit. Okay. So this has become redundant, which can be removed from the system itself, because between in the same point, no, same point is connected to the capacitor, two plates of capacitor. It will not store any charge because potential difference itself is not there, right? So that means what? That means you have to only consider this capacitor C1, which is this one, which is in between A and B, and this is what is C equivalent. So C equivalent is nothing but C1, which is 4 pi epsilon naught AB by B minus C. Clear? This is what it is. Books, they have derived so much, so lengthy derivation they have given, but they have not got this idea. This idea is a very powerful technique. I discussed in the class also, very powerful technique. Okay, and there was one question advanced level which can be quickly solved using this technique. We'll discuss that. Let us say now that there are three. Now they have given three cells of radius A, radius B, and radius C. Okay, three they have given, and what they have given is they are saying that the middle one is earth, middle one is ground, and the other two are connected. Other two are connected. Here this is a jump. Note that This wire is connecting first and third. It is just crossing over the second one. It is not touching the second one. Okay. So, so this is the first one. This is second one, third one. First and third are short circuit means they are just connected. They will have same potential. Okay. Right. So, what will be the potentials of this potential? So, this V1 will have some potential. V2 will be 0 here. V3 will be something will be there. Now again use the same technique. What is the technique? Keep a capacitor at infinity. Okay. Keep a capacitor at infinity. This radius has infinite radius. And this, let us say this is fourth. So V4 is equal to 0. Okay, V4 is 0. Now try to make capacitances, because capacitance is always in between two plates. Okay, between two plates. So between the first and second, this capacitance is C1. Between first and second, between second and third, this is C2. Between third and this fourth, C3. So now there are three capacitances here. We want to find the equivalent here. So what I told you, draw a equivalent circuit considering them as parallel plate capacitor. Okay, draw that. So V2 and V4 are equal. Okay, V2 and V4 are equal. So let us draw this point as V2 and V4, which are equal to 0. What are other 2 points? Other 2 points and V1 and V3. V1, V3, you do not know where it is, but somewhere let us keep this as V1 and let us keep this as V3. Okay, these are some. So there are basically three different points having different potentials. Okay, now this capacitor C1 is between V1 and V2. V1 and V2. So draw one capacitor between V1 and V2. V1 and V2. Uh, Let me just keep this point somewhere else, right? Somewhere here V3 I am keeping. So, but V1 and V2 I will draw one capacitor which is C1. Then C2 is in between V2 and V3. So, V2 and V3 I will draw another capacitance. We can draw, this is what is C2. Okay, over. And C3 I will draw between V3 and V4. V3 and V4 I have to draw again another one. V3 and V4 means I have to draw one more capacitor like this, right? This also I have drawn. Let me just redraw the circuit, not looking good. Okay, structure I will just change. So this point I am taking V2, V4 equal to 0. This I am taking as V1 and this I am taking as V3. Now you see it will look easy. So between V1 and V2 there is one capacitor like this. Between V2 and V3 there is C2, so this is C1 and there is another C2 here, and there is one more capacitor C3 between V3 V4. There is another capacitor like this C3, correct? Now you see we have these points. Now it is looking better. Okay, so what is the equivalent now? Equivalent we have to calculate. How do we calculate equivalent? Equivalent means between this point, between 1 and 3, what is the equivalent? So series parallel, try to use series parallel you use. And before doing series parallel, also write C1, C2, C3. Write that. Write the value of C1, C2, C3. What is C1? C1 is between 1 and 2, so it will be 4 pi epsilon naught AB by B minus A. C2 is in between this and this, so C2 will be what? C2 will be 4 pi epsilon naught BC by C minus B. C3 will be what? C3 is between this and infinity, so it is 4 pi epsilon naught C. That's all, right? So C1, C2, C3 you have written using the formulas. Then now apply this. C equivalent now applies from circuit. What is C equivalent? C equivalent, these two are parallel. So what is the equivalent of this portion? What is equivalent of this? Tell me. This equivalent will be, they are in parallel, na? So it is C2 plus C3, correct? This. So this one and C1, they are in series. These two are in series now. Are you understanding? Because C2 and C3 are parallel, so their equivalent is C2 plus C3. This C2 plus C3 becomes series with C1. Okay. So now you find C equivalent. C equivalent will be or 1 by C equivalent you can calculate. 1 by C equivalent is 1 by C1 plus 1 by C2 plus C3. Correct? Like this you calculate. Now we know this value C1, C2, C3. Now let us substitute and calculate. So 1 by C equivalent, and also note that where have we given the charge? 1 minute. Where have we given the charge? Here charge was given or not given? Somewhere some charge must be given. Somewhere they will give some charge, okay? Don't worry about that. They will give some charge. One thing we missed out here. What is that? Can you say what we missed? See, we missed out considering that they are connected here, right? They are connected now. They are connected means they have also same potential. Oh, so redraw that circuit. That means point 1 and 3 are same points. Point 1 and 3 are redraw this. Okay. Point 1 and 3 are same points. Okay. Point 1 and 3 are same because they are same potential. Na? Same potential. So now basically there are two different points. One is point 1 and 3 are same. Point 1 and point 3 are same point. And what about other? V2 and V4 are same. V2 is equal to V4, that is equal to 0. Okay. So now you try to put capacitor. So C1 is between where? C1 is between 1 and 2. Between 1 and 2 you put C1. Okay, then C2 is between 2 and 3. 2 and 3 means this only. So try to put here another capacitor C2. C3 is between where? C3 is between V3 and V4. V3, V4. Oh, all are coming parallel. All are coming parallel. Yes? Are you getting this? All because these are no, they are joined na. Because they are joined, so V1, V3 you have to take same potential. Okay, then it is good na, easy na. All parallel means simply add them. So C equivalent of this system will be just C1 plus C2 plus C3. Okay, add them. So it is very easy to add na. You take common 4 pi epsilon naught will come common. First of all, 4 pi epsilon naught you take common. 4 pi epsilon naught I take common. Then here what it is, AB by B minus C. It will come AB by B minus C plus BC by C minus B plus C, right? That's all over. This is now you simplify this. Okay, now you simplify this. So 4 pi epsilon naught AB by B minus C. Here I will take LCM C minus B. So C square and BC will get cancelled. It will become C square. So this is the answer. This is the equivalent of this system, and this is a good technique to do that. But only thing is that take care which points are same and which points are different, and redraw, make a parallel capacitor. Clear? Yes. Okay. So this is done. Then you can start solving questions on series and parallel, calculating the C equivalent, how to calculate C equivalent. So I will give some methods of C equivalent, how to calculate C equivalent. Methods of finding C equivalent. Methods of finding C equivalent. So basic method, series, parallel. Now you know if they are in series, then 1 by C equivalent is 1 by C1 plus 1 by C2 plus 1 by, right? If they are in parallel, so it is just sum. C equivalent is C1 plus C2 plus like that. But if they are neither in series nor in parallel, there are some special techniques which we have to learn. So there are some 7 or 8 techniques are there, going from very basic level to advanced level. Okay, so let us discuss those techniques. So first is called method of same potential. Very important technique, method of same potential. Same potential. If you can learn this technique, then you can solve most of the question in NEET. Okay, because mostly the question in NEET which are coming is based on this method of same potential. So let us try to understand with this example. Okay, so what you need to do is you have to just label all points with, you know, uh, label all points with some symbols. You have to label with different potential. Let us say different potential, different potential, and redraw the circuit. Redraw circuit. So now if you do this two step, the circuit will become simple series and parallel. I'll give the example, very simple example. Let us try to take example. There is a capacitor, there is another capacitor, there is another capacitor, there is another capacitor. 4 capacitors are there. This is point A and B. And now what they are doing is they are saying that this point and this point are connected, and this point and this point are connected. Each capacitance are CCC. Each capacitance is CCCC. Now they are asking find the equivalent capacitance between A and B. Find equivalent between A and B. How do we calculate that? So what is the first technique? Try to label all the points with the potential, name them. Okay, so you can label like this. Suppose I say that this point is point 1. Now note that any point which is connected directly to that point will be having same potential. So if this point is 1, this point is also 1, this point is also 1, this point, all these are same point, 1 1 1 1 1, right? Understanding? Okay, so all those points are the same point, 1 1 1. Okay, suppose if I say this point is 2, then this points is also 2, this is also 2, this is also 2, this is also 2. Okay, and I will say this point as 3. That's all. So there are basically 3 different points. Can you understand this? Now redraw the circuit. So you have labeled all the points with different potential. Whichever are different, they will have different name. Whichever are same means that is same. For example, this 1 1 1 1 all are same on. Okay, now redraw the circuit. Redraw means how many different points are there? There are 3 different points, 1 2 and 3, and you want you want C equivalent between A and B, means between 1 and 3. Between 1 and 3 you want. Redraw the circuit. So 1 2 and 3. Okay, now let us try to make capacitor between them. So this first capacitor is in between 1 and 2. This capacitor is between 1 and 2. So draw one capacitor between 1 and 2. So this is over. Now second capacitor. Second capacitor is between 1 and 2 again. So draw again one capacitor more between 1 and 2. Draw again. This is also over. What about this? This is also between 1 and 2 only. So draw another one. Between 1 and 2, draw another one. Over. What about this capacitor? This is between 2 and 3. So between 2 and 3, draw one capacitor. Done. Are you understanding this? Then the game is over, because you can clearly see that in between 1 and 2 and 3, these 3 C C C are in parallel. So this parallel will give C plus C plus C, and this is another C. So this 3 C plus C plus C means it has become 3C. So between 1 and 2 you can write equivalent as 3C. Between 2 and 3 there is only 1, which is C only. So now these two capacitors are in series. So done, over. right? So series means you calculate C equivalent. So product 3C into C by 3C plus C also you can do. So this will become 3 by 4C. Clear? This is how we will be solving problems. So method of same potential, very very powerful method, very very important technique is there. It may not look like it looks like all everything is series, but many of them are parallel and one is in series. So if you redraw the circuit by labeling, you can solve a lot of questions. Okay, then so this technique you will be using. Then let us go to the next method. Second method is method of connection removal. Connection removal. So let us take example. This is point A and this is point B. Let us say that this is C1, this is C1, this is C2, this is C3, this is C3, this is C4, this is C4. So in such circuit, you can see that if you send some charge Q, same charge has to come out Q. So in between A and B, you have to calculate C equivalent. Okay. So you can see here that there is a, suppose you are sending some charge and let us say this charge breaks as Q1 and Q2. Note that there is a symmetricity about this point. Can you see that there is a symmetricity? Yes. Because this C3 is C3, this C1 C1, this C4 C4, they are like mirror image. This is like axis of symmetry. So whatever left of this side is same as right of that side. That is a mirror image. So whenever there is mirror image, we can apply this, right? So there is symmetry in input and output side. So if you are giving Q1 Q2, so here same Q1 must come in this branch and same Q2 must come in this branch. Similarly, suppose this Q1 which is going here will split into Q3, Q4, Q3. So same Q4 must come here and same Q3 must go here. And this Q2 which is coming here, this Q2 is directly going here. That means what? This is a very important idea. That means at this junction, at this connection, this Q2 is not getting divided in the upper branch. And this Q4 which is coming here, now you can see that this Q4 which is coming here, now this Q4 is directly going like this. Okay, without any breaking. And similarly this Q2 which is coming here, it is not breaking, it is directly going here. That means this junction or this connection can be removed because it is not breaking any charges. So connection removal means remove this connection, just lift this up. So you can redraw this circuit. Now I see, you can see that this connection has been lifted up, right? This connection is lifted up. So because there was no charge, charge was not breaking. Now this circuit become very simple circuit. Can you understand how it has become simple? Yes. How this has become simple? It has just become series and parallel. It just becomes series parallel. Why? Because these two C3 are in series. You can see that this C3 are in series. This equivalent will be parallel with C2. Yes, this parallel with C2. And once they are parallel, that equivalent is in series with C1. Their equivalent is parallel with this branch. Clear? Yes. So this become a very simple, way to solve problems. Method of connection removal, it's an important method. Okay, fine. So today we have discussed up to this much. Then there are more methods are there. We will be covering tomorrow. Probably we'll do that, right? So you can start working out problems on capacitance, right? Okay, fine. Then we'll see next class. Bye bye tomorrow. Okay.